welcome back to another Orange Coast College mathematics video. Today we're going to be learning about composition of functions. Now, the composition of f and g is going to be denoted by f, this little circle, and then g. That little circle literally just means of. So, if you see f, little circle, and then g, really you'll read that as f of g. Now, I'd like to remind ourselves of what a function is actually doing. So we can treat functions as these little small machines where I'm going to plug in some number, which will be an input, and it's going to spit out an output. Now, the idea of the composition of functions is that what happens if I have two separate functions and I want to use one of those functions as the input for the other. So I do f of g of x, as in g of x is the input to my function f. So if I have f of g of x, really what I'm saying is I want to plug in g of x into my function f. So the domain of my composition of functions, f of g, is going to be the set of all the numbers that are already in the domain of g, such that when I plug that number x into g and then I get an output, it's not going to be a problem number for my function f. So moving down to our first problem, we are given that f of x is equal to x plus 1 and g of x is equal to x squared minus 2x. So I want to find the composition f circle g, as in f of g. So f is going to be the outside function, and g is going to be my inside function, the input of my function f. So I'm going to essentially copy-paste whatever's inside my parentheses and plug it in wherever I see an x in my function f. I have g of x as my input, so I'm going to plug in g of x wherever I see an x in my function f. And so we get the composition f of g of x is equal to g of x plus 1. Now I know what g of x is actually equal to, right? It's equal to x squared minus 2x. So I can plug that in and I will have x squared minus 2x plus 1 as my answer. Now I can get rid of my parentheses to make this a little bit cleaner. So we get a final answer of x squared minus 2x plus 1. And so we've just found the composition of functions. Now we can actually do it the opposite way. We did f of g of x, and now down here for part B we can see that we can use f as the input of g. So we can write this, g comes first, so it'll be g of f, as in f is my input. And so we write g of f of x, and so now f of x is the input. So I'm going to plug in an f of x anywhere I see an x in my function g. So this is going to be f of x quantity squared minus 2 times f of x. Now I know what f of x is equal to. It's equal to x plus 1. So I can substitute that in anywhere I see this f of x. So we get x plus 1 quantity squared minus 2 times x plus 1. Now I can FOIL this out, and I'm going to get x squared plus x plus 1. Now be careful, we want to make sure that our negative 2 distributes to both pieces. So we'll have minus 2x minus 2. Now I'm going to group these pieces together. So I have x squared plus 2x minus 2x, and then I have plus 1 and minus 2. So now I can combine like terms. I see that I have a positive 2x and a negative 2x, so those are going to cancel out. And I have a positive 1 and a minus 2. So when I add those together, I'll get minus 1. So we get a final answer of x squared minus 1. Now into problem 2. We have two functions. We have f of x equals 5 over x minus 1, and g of x is equal to 4 over 3x minus 2. Now, the question is saying we want to find the composition of f of g of x and its domain. So, just as a reminder, we have f of g. So, I want f with g of x as my input. Now, I'm going to put g of x anywhere I see an x in my equation for f. So, this is going to be equal to 5 divided by g of x minus 1. But I know what g of x is equal to. G of x is equal to 4 over 3x minus 2, so I can plug that in appropriately. So I'll have 5 divided by 4 divided by 3x minus 2, and then that whole thing minus 1. Now, whenever I have a fraction minus a number, usually it's good practice to get these two into the same fraction itself. However, in order to do that, I need to make sure that they have the same denominator. So what I'm going to do is I'm going to multiply by what I like to call fancy 1. As in, I'm going to multiply by 1 in a creative way so that I can combine these things together. So if I multiply by 3x minus 2 divided by 3x minus 2, I'm really multiplying by 1, so I'm not changing my equation in any significant way. However, I am making it look a little bit different, as in now, both of these pieces have a denominator of 3x minus 2. Since they have a common denominator, I can combine them. So we'll have 5 divided by 4 over 3x minus 2 minus 3x minus 2 divided by 3x minus 2. And we can combine this further because now they have the same denominator. So we're going to have 5 divided by 4 minus 3x plus 2, all divided by 3x minus 2. So we have something divided by a fraction. And how do we deal with that? We multiply by the reciprocal. This is going to be equal to 5 times the bottom fraction flipped. So this will be 3x minus 2 divided by negative 3x plus 6. Now if we actually just multiply that through, we're going to have 15x minus 10 divided by negative 3x plus 6. And that is our composition of functions. However, we're not quite done. The question also wants its domain. So how are we actually going to find our domain? Well, we're going to start off by finding the domain of our individual functions respectively. So let's start off by finding the domain of f. So the domain of f is going to be all the numbers such that we're not dividing by 0 or we don't have a negative in our square root. So the only number that's really going to give us a problem with our function f is 1, because if I plug in 1, I'm going to have 1 minus 1, which is equal to 0 on the denominator, and we're not allowed to divide by 0. So my domain is going to be all real numbers except 1. So negative infinity to 1, union 1 to positive infinity. Now let's look at the domain of g. What numbers are going to give us a problem for g? Well, we don't have any square roots, so we don't have to worry about getting a negative anywhere. So the only real problem is going to happen when 3x minus 2 is equal to 0. Because if it's equal to 0, that means we'll be dividing by 0, which we're not allowed to do. So when is 3x minus 2 equal to 0? Well, we can solve for that. 3x minus 2 being equal to 0 implies that 3x is equal to 2, and hence x is equal to 2/3. So I can't plug in 2/3 into my function. So the domain of g goes from negative infinity to 2/3, union 2/3 to positive infinity. Now, one of the things we're going to have to be careful of is not just smushing these two domains together in order to get our domain of our composition of functions. We have to be careful because one of them is an input. As in, g is my input for my function f. So, if f is not allowed to plug in the number 1, that means my output of g is not allowed to be equal to 1. So I have to individually figure out where my function g is equal to 1. Now that will tell me what numbers I'm not allowed to plug in. So how do we figure that out? All we have to do is set g equal to the problem numbers of f. So I'll do 4 over 3x minus 2 is equal to 1, because 1 is the only number I'm not allowed to plug into my function f. So we can multiply both sides by 3x minus 2, and we'll get 4 is equal to 3x minus 2. I'll add 2 over, and we'll get 3x is equal to positive 6, which means that x is equal to positive 2. So when I plug in 2 into my function g, I'm going to get a value of 1. Now, because my composition is f of g of x is my input. So if I plug in x equals 2 into g, I'm actually plugging 1 into my function f, which we said is not allowed. So the domain of my composition of functions, f of g of x, is going to be from negative infinity to 2/3 union 2/3 to 2 union 2 to positive infinity. Now that will be our final answer. Now moving down to part B, we see that we have the opposite. Instead of f of g, now we have g of f. So let's write it down. G of f. We have g of f of x, as in f of x is the input to my function g. So I'm going to plug in f of x wherever there was an x in my g. So this will be equal to 4 over 3 times f of x minus 2. Now we know what f of x is. F of x is equal to 5 divided by x minus 1. So I can plug it in. So this will be equal to 4 divided by 3 times 5 divided by x minus 1. And then this whole thing minus 2. I'm going to multiply the 3 through. So we're going to have 4 divided by 15 divided by x minus 1. All of that minus 2. Now we're going to use the same trick of multiplying by fancy 1 to make sure that we can combine the two pieces on the denominator. So I'm going to multiply by x minus 1 divided by x minus 1. This will allow both pieces of the denominator to have the same denominator, and we can combine it. So let's multiply everything through. So we'll have 4 divided by 15 over x minus 1 minus 2 times x minus 1 divided by x minus 1. Now both pieces in the denominator have the same denominator, so we can combine everything. And so we get 4 divided by 15 minus 2x plus 2, all divided by x minus 1. Simplify everything, and we get 4 over negative 2x plus 17 divided by x minus 1. Now, we have something divided by a fraction, so we multiply by the reciprocal. So we have 4 times x minus 1 divided by negative 2x plus 17. Multiply it through, and we get 4x minus 4 divided by negative 2x plus 17. And so we have our composition of functions. Now, again, like the last problem, we're not quite done because we have to find the domain as well. Now, similarly, we're going to start off by finding the domains of f and g respectively. Now, since we've already done that for both g and f, we can just copy-paste that down here. So, we know the individual domains of f and g, but this time the inputs have switched. F is our input to g. So we need to make sure that our f is not equal to the problem number of g, which is 2/3. So how am I going to figure out what x value that is? I'm going to set f equal to the problem number of 2/3. So we get 5 over x minus 1 is equal to 2/3. Now we're going to multiply both sides by x minus 1, and we're going to get 5 is equal to 2/3 times x minus 1. We're going to divide by 2/3, and we get 15 over 2 is equal to x minus 1. Now I'm going to add the 1 over, and so we get 15 halves plus 1 is equal to x. Now I have a fraction plus an integer, so I'm going to rewrite that as x equals 15 halves plus 2 over 2, and so we get 17 halves. So if x is equal to 17 halves, my input function is actually going to be equal to 2/3, which is the problem number for g of x. So we can't include 17 halves in our domain. So the domain of our actual composition of functions, g of f, is going to be negative infinity to 1, union 1 to 17 halves, union 17 halves to positive infinity. And that is our final answer. Moving on to our last problem, we need to look at the composition f of g of x and its domain, given that f of x is x squared plus 1, and g of x is equal to the square root of x plus 2. So like the other problems, let's find f of g of x first. So f of g of x is simply saying that the input is going to be g of x. So I'm going to input g of x anywhere I see an x in my function f. So f of g of x is going to be equal to g of x quantity squared plus 1. Now I know what g of x is equal to. It's equal to the square root of x plus 2. So let's substitute that in, and we get the square root of x plus 2 quantity squared plus 1. Now the square root and the square are going to cancel each other out, and so we'll be left with x plus 2 plus 1. So f of g of x is equal to x plus 3. Now it's time to find the domain of our composition of functions. Now you need to be careful. You might be tempted to say that you can plug anything into x plus 3, and really you're right. However, we need to consider the domain of our input function as well. So, what's the domain of g of x? Now, what numbers can we not plug into a square root function? We can't plug in negative numbers. So, I just need to make sure that x plus 2 is not negative. Now, we can write an inequality. So x plus 2 is going to be greater than or equal to 0. Now, there's nothing wrong with having a 0 in our square root, so we're going to have the equality as well. So solve for x, and we get that x is greater than or equal to negative 2. So the domain of g is going to be negative 2 to positive infinity. The domain of f is all real numbers. Our composition of functions doesn't have any problem numbers. There's no problem numbers in our function f. However, we do have problem numbers in g. So our composition of functions is going to take on the domain of g itself. So the domain of f of g is going to be negative 2 to infinity. And with that, our lesson has concluded. Thank you for watching, and I hope to see you in the next one.